Streaming is preparing to live stream. And let me share my screen. Share screen. Share. Okay.
Yeah.
So while I'm doing this, I can't see anything. So Junbom, please let me know if attendees do show up. I'll
Okay.
use my other computer to look at the clock.
Sure. Our webinar is showing up on the Claudia page.
Perfect.
And how many audience? We have 3 audience.
Fantastic.
One is he is Jeji.
Yep.
Oh.
Hi, everybody. This is going to be a very informal presentation session. We're going to get started in 4 minutes with our first contestant, but I will introduce this in another minute or 2. So just hang tight. I wish I had background music to play, but I'm not that professional.
We need 2 more judges to come.
For those of you just joining us, my name is Andrew Bagel. Junbom, you and I are running the ACM Student Research Competition at ICSE 2020 this year, and this is the technical presentation round. We'll get started in another minute or so please hang tight. Okay, I'm going to get started. Thank you everyone for joining us at the ACM Student Research Competition Technical Presentation Round. This is round 2 of a competition that started out with 18 contestants. These are students who are graduate students or undergraduate students in universities from across the world who have made entries with their research. First, they presented, they wrote a short paper about their work that was evaluated by a program committee several months ago. 18 of those contestants were approved for the conference. And yesterday, July 8th, on Wednesday, through 3 different time bands, we held a virtual poster session. And from that poster session, we have selected 9 participants across the different time bands to participate in the technical presentation session. 5 of them are in the graduate student category and 4 of them are in the undergraduate category. Today, We have 3 contestants who will be giving talks, and the judges should be attending right now in the webinar. For each contestant, once the instructions for you, basically when it's your turn, please share your screen, unmute your microphone and your video, and then make a 10-minute presentation. And you'll have 5 minutes of Q&A from the judges. The judges will type their questions into the text chat, and then I will read them out loud to the contestants. And then when you are responding, please just respond out loud so everyone can verbally hear you. Judges, please use your score sheets and evaluate the presentations. Please ask questions during the text in the text chat during talks. And then when we're all done, please email us your score sheet as soon as you can so that we can enter it into our total spreadsheet. Today we have, looks like 8 judges attending, 7 or 8 judges. So we'll have lots of good evaluation and feedback. And our 3 contestants today are Tegan Brennan, Rangeet Pan, and Zhufang Zhu from a variety of different universities. And I'd like to introduce Tegan Brennan from UC Santa Barbara, who's a graduate student, and she's going to be talking about the detection and mitigation of JIT-induced side channels. So now I will let Tegan take it away. And everything looks good, Tegan. Go for it.
Great. Hi, everyone. I'm Tegan Brennan, a PhD candidate from the University of California, Santa Barbara. Today, I'll be presenting my work on the detection and mitigation of JIT-induced side channels. In general, side channels in software arise due to observable differences across program pods. As an example, consider the equals function here. This function compares a guess and a stored password character by character. As soon as a mismatch is detected, this function returns early, introducing a side channel in time that allows some observer to determine how many characters of the guess match that of the stored password. We can experimentally check this side channel. Here I show the results of 2 different experiments. The violin plot in blue shows the execution time behavior of this function when it is run on guesses whose first character does not match that of the stored password. The violin plot in green shows the execution time behavior when the first characters do match. These 2 execution time distributions are distinguishable, illustrating the side channel we hypothesized about earlier. This side channel was due to the early return in the previous function. So to fix it, one might think, well, how about we remove that early return and instead ensure that the same amount of work is done regardless of whether the characters match. As a result, a developer might produce something like the equals safe function that we see here. But is this function really safe? Once again, we can experiment. Here I show the results of the same 2 experiments run on this new version of the equals function. Now these 2 execution time distributions appear to be indistinguishable. So is the side channel really being eliminated? Well, there's one crucial bit of information that I've kept from you, which is that I ran these experiments with just-in-time compilation disabled. When I run the same experiments, this time enabling JIT, the story has completely changed and a side channel has arisen. This timing side channel is due to just-in-time compilation. As just-in-time compilation attempts to optimize pods that it deems hot, it can introduce timing side channels even into code that appears to be balanced at the source code level. The reasons for these side channels are an imbalance in the input distribution to the program, leading the runtime to favor certain program behaviors. Now, just-in-time compilation is critical to the performance of many modern programming languages. Therefore, it's essential that we understand these types of vulnerabilities that just-in-time compilation can introduce. In some of my previous work, I have worked towards understanding 3 key aspects of JIT-induced side channels: when they can arise, what types of information we can actually learn from them, and how an attacker could effectively go about exploiting JIT-based side channels. To address the first question of when JIT-based side channels might occur, I've introduced 3 different attack models that categorize scenarios where they might arise. To answer the second question of what one might learn via a JIT-based side channel, I've introduced 5 different vulnerability templates which categorize code segments containing predicates that might be vulnerable to be learned via a JIT-based side channel, as well as the JIT optimizations responsible for causing these side channels. Using parameters and strategies from these vulnerability templates and attack models, I answered the last question of how an attacker might effectively exploit JIT-based side channels by developing a 2-stage algorithm. I first evaluated my work on built-in Java and JavaScript functions and found there to be significant leakage due to JIT-based side channels in both. I then turned to larger case studies on open source projects. One of these is Graph-Hopper, a routing library similar in use to Google Maps. In these experiments here, I show how some observer, timing only their own interactions with Graph-Hopper, can actually tell if and when some other user makes an atypical query of the system. In this case, an atypical query is one where the source and destination are sufficiently distanced. Remarkably, this side channel is actually large enough in magnitude that it was detectable even across the public internet. While these results were encouraging, there was still manual effort that went towards inducing these JIT-based side channels. Therefore, I next turned my attention to the automatic induction and evaluation of JIT-based side channels. My technique essentially fuzzes the runtime into many different program states, and then evaluates each state for side channel vulnerabilities. My approach requires a strategy to introduce new runtime states, as well as a technique for evaluating the vulnerability of those states. To address this first concern, I automatically generate priming input. Priming input is program input that is sent repeatedly to the runtime in order to prime it to favor certain program behaviors. I automatically generate this priming input using the fuzzer AFL. Though AFL doesn't make any guarantees in terms of coverage, empirically, I found it to be effective in generating input that covers many different program behaviors. Second, I turn my attention towards generating pairs of evaluating input. If pairs of evaluating input sets are separable via their execution time behavior, then a side channel in time has resulted in the runtime. In generating evaluating input, I ideally want to find partitions of the input space that are most likely to be separable. Returning to our running example, we can gain the intuition that these are partitions of the input space that differ on some secret dependent branch. The first step in my process of finding evaluating input is to perform dependency analysis to mark all branch conditions that depend on some secret input. To the right, I show the program sanity safe. This program takes 2 input, one of which, an integer a, is marked as secret. Then I develop an instrumented version of the program under test. For every branch condition in the code, I introduce an integer variable, which is set to 1 if that branch is taken, and otherwise set to 0. I also introduce an integer variable for every loop in the code, which is incremented with each subsequent loop iteration. The end result is an instrumented version of the program under test, which, for any given input, produces a set of tuples which define the behavior of the program at branches and loops for that particular input. Using this instrumented version of the code under test, I produce input tuple pairs. Then I match those tuples to a set of predefined patterns in order to partition the input space into sets. At a high level, these patterns attempt to partition the input into 2 sets that differ on some secret dependent branch, but agree as much as they can elsewhere. With this priming input and evaluating input in hand, I now turn to systematically fuzzing the runtime. Here, I prime the runtime in favor of each priming input in turn, and then use my pairs of evaluating input to determine if a side channel has arisen. I evaluated my automated technique on the Blazor, Themis, and difffuzz datasets, which are widely used for side channel detection. These datasets each consist of 2 types of programs: the original programs containing a side channel vulnerability, and their fixed, supposedly safe counterparts. While I experimented on both, I show my results on the safe variants here. I was able to automatically introduce JIT-based side channels in the majority of these programs. In the Blazor dataset, I was able to introduce JIT-based side channels in 13 of the 14 supposedly safe programs, a result which directly contradicts that of 4 state-of-the-art tools for side channel detection. At present, I have turned my attention towards the mitigation of JIT-based side channels. As previously mentioned, just-in-time compilation is crucial to the performance of many modern programming languages, such as Java and JavaScript. So simply disabling JIT is not a realistic option. Instead, I turn to ideas from differential privacy to address this problem. In a traditional differential privacy formulation, we consider 2 databases that differ by 1 entry, and we want to ensure that any aggregate query over these databases must be indistinguishable. In doing so, we introduce a trade-off between privacy and accuracy. In my extension of differential privacy to runtime systems, I'm considering 2 input histories that differ by 1 input. I want the execution time behavior of the runtime resulting from those input histories to be indistinguishable. And in doing so, I introduce my own trade-off between privacy and performance. This concludes my talk, and I would be happy to take any questions or comments that you have for me now. Thank you.
Thank you very much, Tegan. That was a great talk. We have one question so far. So I'm wondering, what are the specific contributions of the submitted work as different from your prior publications?
Yes, absolutely. I mean, I think the key contribution is my current work towards the mitigation of JIT-based side channels. Currently, I'm experimenting not only with the differential privacy policy I've mentioned, but also with several other different compilation options in an attempt to preserve performance while minimizing leakage.
Great. Now, let me ask a question of my own. Can you give us a real-world example of a particular leak that could have resulted from a JIT-induced side channel?
Mm-hmm. So currently in my own work, I've been able to introduce leakages into not only Grasshopper, but also the Apache Shear authentication framework. Currently, the results that I have, I think, are really strong results in terms of demonstrating leakage. But one thing I think that remains to be done is really finding a security critical application where a JIT-induced side channel is used to recover some truly sensitive data. So that's still work that remains to be done, but I think with the implementation and engineering effort, it's definitely possible, especially with JavaScript browsers.
Thank you. Does your approach work for other languages besides Java and JIT language, like JavaScript type languages?
I believe at a high level, the approach would work for other languages as long as they have some sort of dynamic compilation component. However, there are definitely aspects of the implementation. For example, I use the fuzzer AFL, which I interface with Java through Kalinchi in my work. So certain aspects of the implementation would have to be modified in order to support other languages.
And how much of an implementation effort was this on your part versus using pre-built libraries that you could find like in open source?
Definitely a combination of both. I use, as I mentioned, AFL, and then I also used a tool called Janalyzer to perform dependency analysis. The program instrumentation and pattern matching were developed by myself, as well as the sort of entire tool chain to link the various technologies together.
Great, thank you. Do we have any other questions from the judges or from any of the attendees? Feel free to type it into the text chat. We'll just wait one more minute for questions. And otherwise, Rangeet can get himself ready.
Mm-hmm. I can stop sharing my screen if you'd like to set up.
Sure, that'd be great. Thank you, Tegan.
Sure.
All right, that's. I'd like everybody to thank Tegan Brennan for her talk today. Thank you very much.
Thanks, everyone.
So Our next speaker is Rangeet Pan, who is from Iowa State University, who's going to be talking about does fixing bugs increase robustness in deep learning? So take it away, Rangeet.
Hi, everyone. Just can you see my screen?
Yes, we can see it.
Okay, thank you. So today I'll be talking about the does fixing bug increase the robustness in deep learning. So I am a second year PhD student at Iowa State University. My advisor is Rajan. Currently, I'm a research intern at Microsoft Research, working with Dr. Nachi Nagappan and Shubhendu Lairi. So before focusing on the work, one question can be, why deep neural network? So because deep neural network is everywhere now. A chart on the left-hand side shows the tremendous increase of popularity of machine learning and deep learning in the last couple of years. The chart on the right-hand shows the increasing number of publications with the top topic deep learning. And deep learning are added to the safety critical system, for example, autonomous driving, aviation system, and medical analysis. Thus, testing and verifying the system that uses deep learning is becoming important. However, deep learning is vulnerable to bug. The left-hand side is the image is taken from our previous study published in eSecurity 2019, and also the right-hand side is from a study in the XC20 by the Zhang et al. So those study has shown that there are new bugs and challenges emerging in deep neural network. And so before designing the testing and verification approach, it is important to understand the nature of the bugs, their fixing strategy, and the fixes that developer proposes, whether that fixes patterns affect the robustness of the system. To the end, this work makes two contributions. Manually labeled dataset consists of bug fixing and robustness labeled with 5 different libraries from Stack Overflow, and the classification scheme for deep neural network bug fix and the robustness. And we have the preliminary dataset has been taken from our prior work published in the eSecurity 2019. The dataset contains 450 bugs from the Stack Overflow and 555 bugs from GitHub. Among them, we could find the fixes for 320 bugs from Stack Overflow and 347 bugs from the GitHub. And this study, the robustness was done mostly on the Stack Overflow. So in the classification scheme, a pilot study was carried by two PhD students who were familiar with the deep neural network and software bugs by coming up with a classification scheme that has been finalized by a discussion with the moderator. The phase is iterative until the classification scheme has not been finalized by everyone. The second and third author of our XC 2020 paper independently studied the post, and we measured the inter-rater agreement among the labelers using Cohen's kappa coefficient at 5%, 10%, 20%. And the post where there is any disagreement between the raters were further discussed in the presence of a moderator. And we have found that the average kappa coefficient of the study is an 85%, which gives a perfect match. So next, I will shortly describe about the bug fixing classification scheme. First one is loss function. This group of fixes is based on the addition, removal, or update of the loss function during training. Network connection related fixes changes the network connection between the nodes in deep neural network if we think the deep neural network is a representation of graph-based system. Adding layer where the developer fixes some bugs by adding a more layer to improve the performance. Layer dimension where the dimension of the layers has to be changed to make the compatible with the adjacent layers or the input. Data dimension is related to fixed to the similar to the layer dimension, but it is related to the input data rather than the deep neural network layers. Accuracy matrix is being updated where is one of the key parameters to be configured. And data type is similar to a software engine problem where the data type of the inputs does not match with the deep neural network expectation. Activation related function when the activation function has to change in a layer for a better performance. And iteration when for a better performance training process, the number of times the training will run will have to be updated. Other than that, the versioning where the DNN library adapts to a different version of system and the code has to update in order to support that version. API contract is a group of fix adds adapted to the fix incompatibility between the composed operations. Data wrangling, when the fixes add data wrangling things like data shifting or data shuffling. Monitoring is related to a fix that add code to the diagnostic during the training process, typically to print training statistics. Optimizer related fix, when the developer modifies the optimization algorithm. And finally, the change neural architecture, where the whole model has to be redone because the initial model was unsuitable. In this presentation, I'll be talking with 3 research questions. The first one, what are the prevalent fixing pattern in Stack Overflow? This graph shows the different fixing patterns is prevalent in the Stack Overflow, the data dimension, network connection, and data type. And some example like data dimension related fix, when we can see the fix need to modify the dimension from the 64 and 4 into a 4 64 64 is to reshape the channel has been changed. So next question is like the fixes that been provided by the developer, does that affect the robustness? In this study, we have labeled the post that the accepted answers, so whether the fix given by the developer is affecting the learning capability. This is done by empirically. We have read the answers of the accepted answer. People post that after the fixing pattern, they have found that another bugs have come or accuracy has been not up to the mark. So level no change, increase and decrease. One example for no change is the version change, where there won't be any change of the robustness. Some fixes like adding a layer sometimes increases the robustness and increase the learning capability. Even same adding layer can overfit the model and decrease the robustness. And we have found a couple of examples like which fixing patterns are prevalent, and we found that in the data dimension related, the robustness change is the most prevalent one. Some of the example is like one such example here. The simple dropout layer, the fixed pattern was given by the changing the dropout layer value to the 1. How the dropout layer works, it randomly removes the edges from the deep neural network. The value is in the range of 0 to 1, not including 0 and 1. So when the developer using the value 1, the model was giving accuracy 97%, while the fixes suggested to use the dropout at 0.99. That actually ends up removing the 99% of the edges, and that ends up the accuracy becomes 11%. That decreases the robustness. Another thing is the resizing. So in this example, the input image was 190 into 150, whereas the DNN were expecting the image to be 150 to 50. The risk in this kind of fix is the loss of information for input due to resizing. Surprising, this risk is never stated in the fix presented on the bug-free web study. Resizing can be done in 2 ways, downscale and upscale. Here we need to do the downscaling because the expected image is smaller than the actual image size. The downscale in the ends up the deep neural network not learning all the feature, and we have found several research papers where they have mentioned the similar problem. And there are other examples related to the other fixing category that I present in our student research competition paper, and other bug fixing categories example and detailed description is present in the ICSI 2020 paper. So to the end, we have discussed about the why deep neural network study is needed. Then we discussed about our data set and how we classify the bug fixing, and then finally our key finding. Thank you all, and you can ask any question right now.
Great, thank you, Ranjit. That was a great talk. So we have our first question is, how do you define what is a bug in deep learning, and how do you know or verify that one is actually fixed?
Okay, so the bug in deep learning, when we created the data set, we mined the Stack Overflow post with some tags like for TensorFlow. We studied the 5 libraries, TensorFlow, Keras, Caffe, PyTorch, and Thealo. And we used the tag like for TensorFlow related problem, we took all the Stack Overflow posts having the TensorFlow tag. Then we manually verified what the post is about. The post can be about like one post can be the user was not able to install certain package. That's not certainly a bug. But if you find that the user post like when the parameter is changing, the accuracy of the model is not up to the mark, or user having any functional errors. That kind of post we manually verified and labeled it as whether bug or not. And going back, Andrew, can you repeat the next question?
Yeah, how do you know or verify that the bug is actually fixed?
Okay, so in bug fixing, so in the Stack Overflow, there is an option called accepted answers. So when the user who posted the question is satisfied with the answer given by the other user, they accept the answer, or they give upvote the answer. So we took the two path. One is that whenever any post has accepted answer, we take that as a bug fixing as a bug fix to the bug posted in the Stack Overflow. And another, all post doesn't have the accepted answer, so we use the heuristic, like the score of that post is greater than or equal to 5, and which is similar heuristic we use in the various study in the Stack Overflow.
Great. We have one more question. Is there any reason to start the test data set with Stack Overflow? Have you tried any other test data sets? So
our bug fixing is both in the Stack Overflow and GitHub, and the robustness study I started doing the Stack Overflow since this study is basically empirical one to go through the post and understand how the robustness is affecting, whereas the study in the GitHub, the robustness, we actually have to run the model, which is future work we are currently working on. So since the Stack Overflow was a little bit least resistive, so we started with the Stack Overflow to at least have a flavor that whether there is any pattern or not. Since there is, we are extending to the GitHub commits.
Okay, I have another question. Compared to fixing bugs of other types of machine learning, what are the major challenges to fixing deep neural networks?
So one of the other than machine learning, so what we have found that in terms of machine learning, there is not that much different. Is we have a study, it's not published actually. We have studied the different challenges people faced in the machine learning, and the deep learning, the behavior is different. So we studied with the deep neural network library, but there is a significant difference in the software engineering bugs and the deep learning though. That's actually a very interesting question to how there is different in the machine learning and deep learning. Frankly, I am not totally aware of the particular difference, and I will definitely, it's a great research question to study also.
Great, thank you. So imagine you want automated bug fixing tools to fix these bugs. Mm-hmm. Is it possible?
So for that, we actually calculated the p-value across the library, the fixing patterns and this, and we have found that there is not much correlation among the libraries, but there are, like Keras and TensorFlow, their bug patterns are very similar, having a very strongly significant value of strongly significant p-value. So this kind of patterns, actually, if one bug fixing tool can be generated for Keras, that can well be used in the TensorFlow. So that our study is what we are trying to do is want to bucketize all the bug fixing categories, so where there will be a significant pattern people can generate, and they can make some automated tools. Like simply an example, like in the last layer of the dense, instead, people when you are using deep learning, you have to use a softmax function just to get the probability. And this very common pattern is the people use ReLU, which is a linear function. So these kind of very small patterns can be learned and can be used as an automated fix for sure.
Great. All right, we have another question. Rather than classifying the type of the change, do you have any insight related to causality between the changes and their effects?
So yes, so we have. That's part of our Isagavist 19 paper, where we classified, that was the bug we studied. We classified the bugs into the bug types, their root cause, and the impact. So we studied the impact as basically functional, non-functional. In the functional bugs, mostly error and non-functional like performance error or memory problems, or the code is not this kind of division is already there. So we studied that, and we found that there is a very significant correlation among the bugs and their impact on the system.
Great, thank you. I think that's all the questions we have time for right now. So let's thank Ranjit for his talk. That was great.
Thank you.
And we're going to move on to our third presenter, who is Zhufeng Zhu, who is an undergraduate competitor from Peking University, who's going to be talking about towards automated migration for blockchain-based decentralized applications. So please start sharing your screen.
Okay.
It still looks black. I think it took a few minutes when we tested it before the session started. And it says that you started screen sharing now. We're also having difficulty with the bandwidth to hear you again. Hopefully that will resolve itself like it did before, once the screen sharing activates. Don't worry, we have time. This is the third and final presentation for our session today. All right, you can see your video now, Zhufeng. We can't hear you. You haven't spoken. Try talking.
Hello, can you hear me?
Yes, we can hear you.
Okay. Okay.
So now let's.
So now you can see my screen.
Wait a second. Yep, now we can see it. And perfect.
Okay.
Go right ahead. Okay.
Okay. Okay. Hello, everyone. I'm Xiufeng Xu from Peking University. And I'm glad to have this opportunity to share my research on automated migration for blockchain-based DApp. DApp means decentralized application. DApp migration includes two parts. One part is smart contracts migration, and the other part is corresponding front-end migration. Smart contract migration means that the deployed smart contracts are replaced by a newer or changed version with a similar or extended functionality. Corresponding front-end migration is the process of adaptive adjustment after smart contracts migration. The key point is that once smart contracts are deployed on the blockchain, they cannot be modified. So the process of migration is significant. Unfortunately, current solutions for DApp migration still rely on manual verification and operation. So it's really an every-point thing for developers. To overcome this situation, I developed an automate tracking tool for migration called SL, which will detect the changes and return a report to developers, make them make better decisions. For assisting tracking tool locate changes precisely without any omission, I summarized the 6 migration categories and divided them into 16 specific migration operators and classified them into 3 priority levels, like function levels, parameter and return value levels, and tab or name levels. Especially the ICMP, non-payable to payable. It will change the payment in the blockchain. So we need to let developers to know this operator will influence blockchain. This picture displays the general running process of our tool. The first step is AST generation, where JavaScript source file will be parsed into abstract syntax tree format. The second step is front-end call graph generation, where our tool traverses the AST by locating keywords. The third step is generating call graph, which contains both front-end and smart contracts information, like the examples as shown in the picture. This picture shows the actual the app called Kitty Club, the situation of that thing. So the next step is comparing APIs. API means abstract binary interface, which is an inactive protocol between smart contracts and the front end, just like the notion of API in the traditional application. So in this step, our tool utilizes 3-round sort matching algorithm. This algorithm sort API according to the 3 priority levels and compare API before migration with the API after migration to ensure the resource covering all the migrations and provide tuples containing the information of migration. After comparing tuples with call graph, our tool will offer a series of changes information in the report to make developers to see the situation in the blockchain and the migration situations. You can see the STL2 demo interface. You can just enter a path into the input box. The path represents the JS source files and APIs. The report will let the developers know all changes and which front-end function need to be modified and where it is through the relationship that call and be called. So to get better preliminary evaluation, I test my tool in 5D apps with several versions and set 2 benchmarks, precision and availability. Precision denotes rate of effective hints. Availability denotes rate of effective query length. So the precision and availability basically reached 90% or even higher. I think it's great results, and our tool can be a promising tracking tool for the future, the app development. So that's all. Thank you. Any question for me is okay.
Great, thank you, Shufeng. We have one question. Why, once deployed, is it not possible to modify a smart contract program?
Pardon?
Once deployed, is it possible to modify a smart contract program?
The version, the early version changed into the new version. It can be a character for blockchain because everything in the blockchain, on the blockchain, it cannot be modified. So every change in the smart contracts, the app need to know and make it matching to the smart contracts on the blockchain. So that is my answer.
Okay, thank you. Does your analysis work across multiple JavaScript files that are connected or just on single JavaScript files?
I make it both. So it all gets some great some great results, but it's still initial tracking tool. It's initial version of our tool. So there's some future works we need to do, and I will do more works on and share it on the GitHub.
That's great. Are there more questions from the judges? I'm looking at the chat to see if more questions come in. What kind of frameworks did you use to build your analysis? What kind of libraries? What kind of libraries or technical frameworks did you use to build the analysis software?
I built it with currently I use the front end language to build our tool. Maybe there are some do you know the TUFO? TRUFFLE, it can construct a blockchain environment. So our tool can use the front-end language to have some work on the blockchain, that thing.
How scalable is your approach?
I think that scalable is now my initial version can be used great in 5D apps. So my approach can find all changes in the smart contracts, but there has some redundant results. The future work can be to emerge some redundant results together and make it more accurate.
Okay, that's great. It looks like that might be all the questions we have. So I'd like to thank Zhufeng for his presentation today. And I'd like to also thank all of our speakers in the Pacific time band. That's all we have for today. So for the judges, please enter your scores on your spreadsheets that we emailed out earlier and email them to the co-chairs today as soon as you can, and then we can enter them into our scoring spreadsheet. And for all the contestants, we will be able to identify the winners after tonight's Atlantic time band has completed, so probably a few hours afterwards.
Oh, can I have a more seconds? I see the judge say that the robustness.
Oh, that's for no, that's from Rangeet to one of the judges. He's answering a question.
Okay.
Yeah, that's not for you. Sorry.
Sorry. Thank you very much.
No problem. Well, thank you again. And thanks to everybody. This was a nice session, and please come back in 7 hours for the Indian time band student research competition. We will have 4 presenters there as well. And then we'll have 2 in the Atlantic time band. So thank you very much, and have a good evening for those in the United States, and a good morning for those in Asia, and middle of the day for everyone in Europe, or actually middle of the night. So thanks very much, everybody, and we'll be signing off now.